all should see my shared screen. Okay, and we can begin the lecture. So I hope you're all doing well with this craziness. You can see, can you confirm that you can see my screen? The ODEs. Okay. Okay, we have a very special guest today. Professor Rob Stoll is sitting with us in this class. He is from mechanical engineering. And today I decided to revisit where we left off in the last lecture. It was kind of rushed. If you remember, we kind of shoved in some ideas about systems of equations. And remember, we were talking about initial value problems. And I think those are some of the most interesting problems when dealing with ordinary differential equations. When we go to partial differential equations, we'll combine both initial value and boundary value problems. But I decided to spend a little bit more time on systems of ODEs. And in fact, guide you through one way of coming up with these ODEs, how we build them together. And we'll try to reconstruct the epidemic model that we solved last time. We kind of did it very quickly, right? And most of you were still stuck figuring out how to get ODE int working because we were running out of time. So we're going to spend the first half of this lecture today on revisiting the system of ODEs. And like we saw last time on this slide, some examples are like kinetics, coupled processes, etc., but nothing beats a real practical example. Before I get to that example, I want to guide you through the process of designing a system of ODEs that is conservative, where things move from one category to another category. That's, for example, that happens a lot in kinetics or like in conservation systems, like moving water from one tank to another, etc. And I'll start with a simple example. I'm going to consider a department store for lack of any other example, but I think it kind of makes sense. Like I said, population dynamics early on, when we looked at the example of the lobsters and the bacteria, they're like they're like very intuitive and easy to comprehend. So I'll stick with that type of example to describe how the process with ODEs works. And our focus is going to be again on, rather than thinking on in terms of the quantities that we're trying to address specifically, we're going to think about the rates of change of those quantities. So we're going to consider this department store, and this store has a number of people in it, you know, shoppers, employees, solicitors, people hanging out, you know, drinking coffee, eating, shopping, etc. So, you know, there's a bunch of people in there, and let's describe the population in that. Let's describe the population in the department store. We'll designate it by the number n. So that n is the number of people in the store. And I'm going to try to move the video, it's in my way. Okay, so yeah, so we describe by n the total population in the store, and the store has an entrance and an exit. Obviously, that's a realistic store. Now, the rate of change of the population n inside the store is obviously dependent on how many people are coming in and how many people are going out, right? So that population will increase if more people are coming in than leaving, and it will decrease if more people are leaving than coming in. It will stay the same if the same number of people comes in and the same number of people leaves. So let's specifically go through and describe mathematically what that means. So if people are leaving the store, such as depicted in this image, people are leaving the store, then we expect the population to decrease in size, correct? Now, in terms of rate of change, again, we're not thinking in terms of the quantity, which is the population size. Rather, we're going to think in terms of the rate of change of the population size. In this case, we expect that the time rate of change of the population to decrease in time. In other words, that dn by dt, the time rate of change of the number of people in the store, is going to be in negative quantity. And we describe that mathematically as dn by dt is minus some rate of people leaving. And that r is a positive number, and the negative sign enforces that this system is draining people. People are leaving the department store, okay? Now, again, if you remember population dynamics, when we talked about population dynamics, that r does not have to be constant, right? And it typically depends on the size of the population. And one could say, for example, the larger the population is in the store, the more likely that the more people are going to be leaving, right? Because, you know, there's a saturation point, and people, it probably means a lot of people have went in and they're done with their shopping, so they're going to be leaving. And one better estimate for the drainage of the population would be a rate of change that is depending on the population itself. So that changes dn dt from minus some rate, which could be a constant, into a minus coefficient times n, the population itself. So the larger the population, the more people are going to be leaving. And as the population shrinks, the less people are going to leave, right? Okay, so now let's take the opposite of that. Similarly, if people are entering the store, then the population is going to increase, correct? So the rate of change, we expect the rate of change of the population in the department store to increase over time. And mathematically, what that means is that dn by dt equal to some rate of people coming in. Now, again, that rate is going to depend on the size of the population, but not necessarily the population inside the store. Rather, it's going to depend on the population outside the store. In other words, you know, I don't know if you've been to the Gateway, for example, or the Tanger outlets, they tell you, like, you know, 1 million people pass through, you know, come and rent a store over here and sell your merchandise because 1 million people pass through the stores over here. What that means is that the larger the population outside the department store, right, the more likely people are going to come in, correct? So the rate of people coming in is going to depend on the population that is outside of the store. So if we call that population I, and there's a reason to this nomenclature, if we call that population I, then the rate of change could be said to be dn by dt equals some coefficient that adjusts that rate times the number of people that are outside the store at any time, okay? So now we've described people coming in and people leaving. And in reality, a department store or a compartment like this, where there's a population that's changing over time, the rate of change of the population is equal to whatever is coming in minus whatever is leaving, right? And R and R in and R out are both positive quantities. Okay, so now that you have an idea of how we construct these ODEs, we're gonna go together and reconstruct the epidemic model that we discussed last time. It's one of the simplest models, called the SIR model. It stands for susceptible, infected, and recovered. Before I get there, if there's any concern now about how these ODEs are put together, you're taking ODEs now, so hopefully this makes sense. Although probably in math, they may not be describing it in kind of this engineering, intuitive manner. But that's how, when you think about ODEs, think about rates of change, what's coming in and what's leaving, okay? What's being added and what's being removed. All right. So now that department store, if you haven't made that mental jump yet, is essentially just a compartment where things come in and things leave. It's just a box, right? And that's how we can describe pretty much everything in reality and physics. So the basic compartment model for epidemics, and the reason I'm choosing this, this example is obviously, you know, related to the current conditions with the COVID-19 outbreak. This model divides the population into 3 compartments. The first compartment is the susceptible compartment. This is the free roaming population. This is people, you know, going to work, going to school, you know, going to the park, going to play game, going to play tennis, etc. And then there's a compartment of people called infected. Those are the people out of the entire population. So the entire population contains some susceptible people that are moving around. And then if those get infected, we're going to categorize them as infected people in red. And then another category for those who have recovered from the infection. So they start being susceptible. For some reason, they get infected because they interact with one infected person or more, right? And then they live through the infection, they infect others, you know, and everyone in their family, for example, and, you know, their friends and neighbors, etc. And then they recover, right? And so they move into these 3 compartments. Now we're going to apply the what we did with the department store to these 3 categories to try to develop equations that govern a population that contains people that are free roaming, people that are infected, and people that have recovered. So obviously, the first step is to say that, you know, the natural direction for people, for susceptible people, is to become infected, right? That's what happens in a healthy population. if you introduce at least one infected person or there's a virus floating around, the only way for susceptible people to move out of the susceptible compartment is to get infected. So that tells us that the first direction of people moving out of susceptible is going to be a negative number. So D susceptible by DT is going to be a negative quantity, right? And we call that minus R1. Now, obviously, again, like we said for the department store, the more susceptible people there are, the more likely that people are going to get infected. So if you take a population of 2 people in a town or 1 million people in a town, obviously the 1 million people, they're going to have higher rates of higher numbers of infected people. So that rate of drainage from susceptible to infected is actually a function of the number of people in the susceptible category, correct? So we change that minus R1 into minus alpha S. But there's one more thing that we missed here. How do the susceptible people get infected, right? They have to interact with an infected person, okay? And the best way to describe this in an ODE model is to essentially just take the product of the susceptible people with the infected people. And the way to think about this, if the number of infected people is small, okay, then I times S is going to return an intermediate number. But if the number of infected people is large, they're going to infect a lot of susceptible people, right? Because they're intermingled with each other. And then that describes how the rate of change of susceptible people or the rate of people being drained from the susceptible category. That's ds by dt. We call this minus beta I times S. I is the number of infected people and S is the number of susceptible people. Again, the more infected there are, the more people are going to drain from the susceptible population. Eventually, there's an equilibrium that will be reached, and we'll see this once we finish off with the model. Now, these people, we move to the infected. So now we agree that the susceptible population just keeps on draining. So there's a negative rate of change going on over there. Now, with the infected people, there are people coming into the infected category, but there are also people moving out of the infected category. Where to? They're moving to the recovered category. So best we can say is di by dt, the rate of change of infected, is in minus out. Now we know what is coming in, right? We know what is coming in, and that is exactly beta times IS. It's the people leaving the susceptible category, they're moving into the infected category. And it's that exact same number. So whatever number of people leave from the susceptible category, they're going to go into the infected category. And that puts it as a negative rate, okay, as a positive rate, sorry, because we're adding people to infected. But also, people are leaving the infected category, going into the recovered category. So we need one negative rate as well. And that is described as best we can. We just assign a number, a rate at which people are being are recovering, and turns out that is related to the to how long the infection takes place. We just say this is minus gamma I, and that is proportional to the number of infected people, not a fixed rate. Because the more infected people, right, most of them, the larger the number of infected people, the larger the number of people are going to recover. So the rate of recovery is going to be proportional to the number of infected people, okay? And then finally, the rate of recovered people, we're only going to add people to the recovered category, correct? So the right-hand side of the equation for the recovered is going to be a positive quantity, and we know exactly what that is. It's equal to how many people are leaving the infected category, right? And that is gamma I. This is amazing what we did here. We started by just defining 3 categories, nothing more. And we were able to come up with a system of equations that actually is a pretty good representation of how a basic epidemic spreads. And as I've shown you last time, we'll get a chance to play around with this in a few moments. But as I've shown you around, if you solve this system of equations, this is one solution for a certain set of parameters, beta and gamma, that is showing you, if you look at the 3 curves, what I'm showing here on the graph, on the x-axis, you have the number of days since the beginning of an outbreak. And on the y-axis is the fraction of the population in thousands. So, you know, we have 1,000 at the top and, you know, 400 for 0.4, etc. So it's a fraction of a population of 1,000 people. The blue curve tells us the number of susceptible people. The red curve tells us the number of infected, and the green curve tells us the number of those who have recovered with immunity. Now, for this specific problem, I started with 999 susceptible individuals and 1 infected person. So you can't see it on the curve, but you see initially most people are in blue, susceptible, they're freely roaming, and there's just 1 infected person. And then as time goes on, you see what happens. More and more people get infected, and they move from susceptible to red. So as susceptible decreases, red is gonna increase, but also recovered is gonna increase. But there's a delay, right? Because people take time, about 14 days with a cold or this COVID-19 disease. They take some time before they get recovered. And you see the balance as people move from susceptible to red to infected, and then from infected to recovered. You see that transition, and then we hit the peak. In this case, we hit a peak of about 60% people become infected before things settle down. Okay. All right. So what I'm going to do is I'm going to do next a couple of activities, but I'm going to skip on some of the activities because we're really short on time for the semester because of the lectures we had to skip. So I'll leave some of the activities for you to do at home. But now, given these 3 differential equations, I want you to take a couple of minutes and just write down the expression using just the explicit forward Euler method of how we would integrate these equations. So these are 3 equations, right, with 3 unknowns. They're coupled. The equation for S has I in it, and the equation of R has I in it. The equation of I has S in it, so they're coupled. But I want you to write down just as if you're integrating from time step n to time step n plus 1 using the forward Euler method. You got a couple of minutes. I'm going to start my timer over here. Again, if you're in groups, go ahead and work in groups. If not, I want to see you scratching your head and using your pencils or pens. Okay, go. So I cannot put the chat window in front of me. So feel free to interrupt if you're raising your hand. There's no room on my screen to put the chat window, so I cannot see you if you're raising your hand. So feel free to just pitch in, please, as needed. So you're expected to get 3 equations for the recurrence formula, let's say, on how to update an initial state into the next state, a state at n into a state at n plus 1. Okay, use the forward Euler method.
Does it matter if we have beta versus beta over n?
No, so that beta over n is a specific for the model. Just use beta or beta over n. It's just a coefficient. In some forms of the model, we rather than solving for the number of the population, we just solve for the fraction, and that beta over n just disappears. Okay, all right, we are out of time. Let's see. I'm gonna go for, hey, Pietra, do you have an answer for us? Maybe for the first equation for S. Just read it out loud. Pietra, are you with us? Yes.
I don't actually. I was just thinking that the R function will be like each derivative, I'm assuming, because that's what where the unknowns are, right? So like I and S.
Yeah, so that's the right-hand side as we described last time. So Nick Goodman, do you have an answer?
Yeah, I got Sn plus 1 equals Sn negative delta T beta over n I n Sn.
Correct. And then, oops, I showed the answer. All right. And so let's see, Emily, do you want to tell us the answer for the infected?
Sure. So I have I of n plus 1 is equal to I of n plus delta t times the quantity beta over n I naught s naught minus gamma
INSN, right? Because n could be 0, right? But not specific. I naught refers to the initial condition.
Yes.
Okay, and then you have the minus delta t gamma IN. And Dylan, do you want to take the last one for the recovered? Let me unmute you, sorry.
There we go.
There you go.
Plus 1 is equal to Rn plus T
Gamma
In.
Yes, excellent. Okay, that's great. So it is no different when solving a system of equations. It's no different than solving a single equation with the forward Euler method. Because what's great about the forward Euler method is that it's explicit. It results in just an algebraic relation. Everything on the right-hand side is a known quantity. So you should plug in the numbers, and then you calculate the updated value. Now, the next activity we're not going to do, we're going to skip it, but I want you to do it by yourselves at home, and I have the answers in the slides, is asking you actually to take some specific conditions and do a single time step using the formula that you just developed. But we're going to skip that activity right now in the interest of time. But I want to go next into how we can get this into a programmable form using Python. So like we discussed last time in a very fast manner, is we like to write systems of equations in vector and matrix form when as necessary and as needed. And this is no different. So over here, if you organize the dependent variables, in this case, Si and R, into a vector, SIR, and the right-hand sides into right-hand side 0, right-hand side 1, and right-hand side 2, you can write this in vector form, right? And d by dt can apply essentially to every element inside the vector over here. And then you just, when you equate this, you get ds by dt is minus beta over nis, and di by dt is et cetera, just like the original equations presented. And in our nomenclature in class, we've been using phi to represent a generic dependent variable. So in this case, d phi, notice the boldface on phi, which just designates a vector, is a vector of right-hand sides. Now, each right-hand side could depend on all the other variables. So the right-hand side has a phi vector inside it as well. Because notice, for example, the right-hand side for the first equation here depends on the first dependent variable s, and also on the second dependent variable I. So in general, the right-hand side in a system of equations could depend on all the variables in the system, okay? Just keep that in mind. Now, when we Pythonify this, we said we're gonna be using SciPy's ODE_int, and we know how to use it for a single equation. Now we're gonna apply it for a system of ODEs, okay? And you get that from scipy.integrate, like we've done from scipy.integrate import ODE_int. Now, for a system of equations, ODE_int, I'm gonna change nomenclature here because that's the documentation in Python, and I feel it's better to describe that documentation to you, the nomenclature here, rather than you having to try to translate between phi and y. So Python, they just use y for the dependent variable instead of phi. We use phi, they use y. That's it. That's the only mental jump you have to make. And they solve a system of equations of the form dy by dt equals, so y is a vector of y dependent variables. So the first dependent variable is y0, second dependent variable is y1, etc. And that's equal to a vector of right-hand sides, where each of the right-hand sides is also a function of all the other dependent variables. So in other words, y is just simply a vector of dependent variables, y0, y1, y2, all the way to yn. Don't confuse that with the time level, okay? Y at t0 and y at t1 and y at t2, etc. So these designate the equations. So we have n equations over here because we have n dependent variables and we have n right-hand sides. So in other words, that's dy0 by dt equal right-hand side 0. But notice what I put in the parentheses for right-hand side 0. I put the vector of dependent variables y. Okay, so that's in boldface. All right. So let's see how ODE_int looks like. The way I like to write it is solution equal ODE_int. The minimum set of arguments you need to pass to ODE_int are these three arguments: right-hand side, y naught, and t. Now, right-hand side, just like for a single equation, this is a Python routine that must return a vector of right-hand sides of the governing system of ODEs. And the right-hand side routine must be deformed at least in the form right-hand side phi vector, or the y vector, comma t. Because internally, ODE int is going to keep calling that right-hand side and it's going to pass it the entire list of dependent variables. So you need to account for that, okay, in that routine. Y0 is a vector of initial conditions. And finally, time is a sequence. We've been using linspace, sequence of times at which you want to find the solution. So what does this look like for the SIR epidemic model? Simply, for the right-hand side, in the routine for the right-hand side, we're going to return right-hand side 0, right-hand side 1, right-hand side 2, exactly like I'm showing here. Right-hand side 0 is minus beta over n times is, which we'll see it in a second, etc. Y0 is the vector of initial conditions for S0, I0, R0. Now, be very careful about the ordering. You can order those any way you like. You can put them R0, S0, I0. But make sure that your right-hand side returns the right-hand sides in the correct order, okay? So if we put them as R0, S0, Y0, the first right-hand side in the array is the right-hand side of R0, okay, of the equation for R0. So make sure that the right-hand sides are consistent with what you provide for the initial conditions. Otherwise, you're gonna mess up your entire solution, okay? And finally, t is like a linspace from 0 to t end, and however many points you specify, okay? All right, so next, what do we do with the solution that is returned? Last time we kind of saw I did this transpose thing and everyone was confused about it. So let's dig a little bit deeper into this. So when you call ODE int, it's gonna return to you what we can think of as a matrix of solutions. The first column in this matrix contains the solution of the first variable, the first dependent variable, y0, at all the times that we were interested in, all the way from t0 to tn. The second column contains the second dependent variable. So the indexing is offset by 1. So that would be y1, going all the way from t0 to tn, and then all the way to the nth equation, yn, okay? Now, obviously, we're interested in plotting y0 versus time, y1 versus time, etc. So we need to extract the array of y0s at the times t and plot those. And the way you do this is we use slicing, like we've learned to do previously. So y0, you just simply grab all the rows in the first column in the array. Okay, so you call y0 you define y0 as equal to solution for all the rows, that's the semicolon, comma 0. So that gives you the first column, okay, or column number 0. And then same thing for y1, you call solution for all the rows, okay, and for column 1. All right, so refer to those slides. You know, I don't even remember how to do this, so I always refer back to my slides when I want to do it. So there's nothing to be ashamed about if you have to refer to those slides. Just know how these solutions are represented, are spit out of Python. Okay, now finally, one last thing before we get to play around with this model is, what if the right-hand side has other arguments? And like we've seen numerous times, rather than having to reprogram the right-hand side as you change the parameters. So for example, over here, we have 3 parameters to change: the population size, beta, the infection rate, and gamma, the recovery rate, right? So I want to be able to pass those parameters into the right-hand side, so I don't have to go and program the right-hand side every time I want to change. Some parameters. So if the right-hand side has extra parameters, again, the right-hand side should have at least phi and t, and those should be in that order and should be the first 2 arguments. Any additional arguments, you slap them at the end. You just add them at the end. In this case, I'm adding 3 arguments, A, B, C. You could have 1,000 arguments. You can have a vector of arguments. It doesn't matter, okay? As long as you put them after phi and t. Now, what you do in ODE int is you add those arguments exactly as listed in your definition of the right-hand side. So if in the right-hand side you define CBA, make sure in the args of ODE int you pass C, comma B, comma A, okay? So notice they have to match exactly, they have to look identical, all right? So now we can take a breather and play around with integrating the system. Go ahead and download the System of Equations SIR epidemic model with gaps from Canvas. I suppose most of you have already downloaded that. I'm just gonna go ahead and open it on my end. Let's see. So it should be under Jupyter Notebooks. I know last time you downloaded a similar notebook. Discard that notebook and download the new one. I added a few other things to it. So what you will see is something like this. I hope you can see my screen. Expand this a little bit. Okay. So again, I have some boilerplate, NumPy, Matplotlib, etc. Just run those and a description of the model. Now, before, okay, let's see. Is anyone still downloading and uploading that to the Jupyter Notebook server? Let me see. All of you are on board. If you're not on board, please let me know, because I want you to pay attention with me here. Okay. Chat. Almost there. All right. Okay, I'm assuming now you have it. All right. So go ahead, once you download it, go ahead and run the that first boilerplate cell with NumPy, etc. Now, don't get to this cell yet, RHS SIR. Let's first think about how we're gonna call the right-hand side, and then we'll go back to programming that. What I have over here is just some initial conditions that we're gonna play around with. I chose a population of 3,000 people. Initially, I have 10 sick individuals and 0 people have recovered. And that puts the susceptible population as the total population minus the infected. Remember, this is a closed system, so the population is fixed. The sum of S, I, and R needs to be equal to N. That's how I define the initial condition for S. I'm gonna start with an infection rate of 0.6. I don't know what that means really. Typically those coefficients are fit into observed data. And then gamma, that's actually mathematically can be shown. Gamma is 1 over the number of days for recovery. Okay, it takes to recover. So we'll try maybe, let's do 1 over 14. That's the average recovery date for COVID-19 patients. And T end 100 days. Now, when we say d by dt, T doesn't have to be seconds. If all quantities that have a rate of change on the right-hand side, they have minutes, units of hours or days or years, then T could be anything, right? So in this case, alpha, beta, and gamma are defined in terms of per day, infection per day. So our time actually is in days. So we're gonna run this for 100 days. And what I'm gonna do, I'm gonna create first a linear space. T is numpy.lin space from 0 to T end with let's just put, say, 100 days. So our time step size is 1 day, which is pretty large, but ODE is very smart about integrating, so I wouldn't worry too much about stability and the things we discussed last time. All right, and our vector of initial conditions is simply, like I mentioned in the slides, I'm gonna solve these equations as S0, SIR, so I'm gonna provide S0, I0, R0 in the vector of initial conditions. Next, we're gonna call ODE int. Now, I want you to think about filling in this first blank over here. Don't worry about the args, okay, yet. Just fill in this first blank. Just give it a name. Think of a name, okay? So maybe we call it RHS SIR, right? Okay, so we're gonna define this right-hand side in a second. Now, what do we need for this right-hand side? What do we need as we change things in the system? I have to think about the arguments. So right-hand side takes phi, the vector of dependent variables, and time, but it also needs to take some other things. So when you think about the right-hand side for this system, I have a bunch of parameters. There's beta, there's n, so this should be beta over n. Apologize, I'll edit that. So beta over n, okay? So same thing over here. So when you think about the right-hand side for this system, the parameters that we can tune are beta, n, and gamma, okay? So I want those to be parameters that I can pass to my system. So I'm gonna go ahead and just pass those arguments over here. I'm gonna pass beta, I'm gonna pass gamma, and I'm gonna pass the population size n, so that I only need to make a change over here and rerun it rather than having to program it on the right-hand side. Now we can jump to the right-hand side formula, or the right-hand side routine. If you call this something else, my right-hand side, just go ahead and change this to my right-hand side. Now, right-hand side, we said it takes at least the vector of dependent variables. When it was a single equation, it was just that one dependent variable. Now, you should treat this phi as a vector of dependent variables. And we're assuming the ordering S, I, and R. So internally, we know that phi contains S and I and R as a vector. And then the next argument is T. Now, what do we put in the question mark? And I want volunteers now. Emily?
And
Dylan?
you could put in beta, n,
Beta, n, and gamma in that order?
yeah.
Yeah, as long as it's consistent too.
No, you said beta, n, and gamma. They need to be consistent with args over here.
Yeah.
So if you decide to choose beta, n, and gamma, okay,
Oh,
then they
beta,
have to be
n.
n and gamma over here. Because internally what it does, it goes through this list and doesn't treat it as beta, and it treats it as argument 1, argument 2, and argument 3, and passes argument 1 to the argument 1 of RHS, argument 2 to the argument 2 of right-hand side, and so on. So you have to be consistent, what you mean by the arguments. Doesn't matter what their order is, but make sure you're consistent, okay? Okay, great, so that is correct. We need those 3 arguments. All right, so now, to build the right-hand side, and I have already built it here for you, right-hand side for equation 0 is minus beta over n I times s, and then for equation 1 is beta over n I s minus gamma I, etc. But how do we get s, I, and r?
Quick question though.
Yes.
In your right-hand side lines, you have beta and gamma written out as words instead of as Greek letters.
Where? Oh,
like,
yes. Good, thank you. So I can essentially, yeah, good catch. Good catch, Eric, thank you. So beta, gamma, okay? You happy now?
Yes.
Thank you for catching that. Okay, so how do we get S, I, and R? So when we were doing a single variable, we were putting over here F, and then we just use F. But now we have phi. And look at my note here. Phi is the vector of dependent variables containing the 3 dependent variables, S, I, and R, in that order. So how do we get S? This is just an array, guys. Phi.
You index them, right? So
0, yes.
Phi
Phi
1,
and then phi 2. Okay, so think of phi, it's a vector of arrays, really. It's going to be a vector of arrays. Okay, so phi 0 contains, the array for S, and I, phi 1 contains the array for I, etc. Okay, so we're almost there. What do we return for the right-hand side? Now, we need to return 3 right-hand sides. The right-hand side for the first equation, the right-hand side for the second, and the right-hand side for the third.
So would that be just like an array of like DSDT, then DIT, and then DRDT?
Yes, exactly. DSDT, because I just defined this here. I could have defined it as RHS0, RHS1. Remember, these are just arbitrary variable names, okay? So RHS0, RHS1, RHS2. Or if you keep it ds by dt, and di by dt, and dr by dt, just to keep some sense, you just put ds by dt, di by dt, and then dr by dt. I know this seems mysterious, but it just works. as long as you are consistent in your ordering. And that ordering starts from how you pass your initial conditions. Make sure your right-hand sides are consistent with the ordering of your initial conditions, okay? All right, so now we go back to solution. Now that we've solved the system, we need to get S, I, and R and plot them. Here, we're so close, all right? So I just discussed this on the slide. So let's go back on the slide because we probably don't remember. Okay, there you go. So Sol contains, the solution contains like a matrix whose columns are the entire solutions at all the times. So the solution for Y0 is contained in the first column. In other words, the solution for S is contained in Sol. We take all the rows on column 0, and then same thing for I, column 1, same thing for R in column 2. Okay? All right. Do we have the guts to run this? I ran it and worked on my end. Let's see. Who, I believe phi is Y0. Yes, Andy, sorry. I'm not able to pay attention to the chat. I know many of you are chatting with me. I'm sorry, please just speak up. Because the chat window is not, it's like hidden somewhere.
Good
okay.
Question.
Yeah, Eric.
So in our line in so in Sol equals ODE, when we call ODE in our args, we also then have beta and gamma as Greek letters.
Yeah, it doesn't matter because that gets passed as a number, right? And then if you change the name in the right-hand side, it doesn't matter. It's just going to bring the number in and assign it to the variable spelled out beta, B-E-T-A, and then it will use that inside it. It doesn't have to be the same name.
Okay.
Because the scope is local. Emily.
Sorry, I have a syntax error, and it's that the Y naught is equal to S0, I0, and R0.
What is the syntax error?
It just says invalid syntax.
And you have the square brackets?
Mm-hmm.
Can you copy the code that you have? Did you run all the cells? Well, it should just run because this is just a Python list.
Yeah, I'm still getting the same error.
Okay, can you copy it to the chat window for me, please? And if we can't debug it now, we'll debug it. We'll debug it privately later if you want.
Okay.
But you should. Okay, everything else looks. It's hard for me without sharing the screen. I mean, in class I would be walking around, right, and I could see what you're doing. But if this is not working. So try this. Can you at least define a list? Like try to do A equal 1, 2, 3, and then print A.
Emily,
if you're able to do that.
I think you're missing a parenthesis in your T.
Yeah.
Over here.
It's in your T.
Your T vector.
Oh, yeah.
It looks like you're all missing a parenthesis in your T.
Yes, it works.
I think you left. I think you kept
Thank you.
T and as is. Okay, good. Thank you, Kevin. All right. Okay, so does anyone have this running now? Does everyone have this running? Anyone doesn't have it running? Okay, great. So now oh no, I see you sent out. Yes, you have a missing parenthesis 100. Okay, didn't see the chat window too. Okay, so now these are the conditions, right? We ran with beta is 0.6, gamma is 1/14, etc. So one thing you would do first is, as you're exploring a system, just put in crazy numbers. What happens if you put beta very small, right? So the infection rate is very low. Let's go to like 0.001. Intuitively, what we expect is infection rate is so low that we're barely going to see any infections going on, right? So let's go ahead and run that scenario. What you get is pretty much nothing, right? No infections going on. I mean, you can plot this in a semi-log Y, and you'll barely see a bump in infections, right? Okay. So the opposite case would be to go with a very large beta. So maybe we'll go for beta is 1. What you see is a quick spike early on, right? A very quick spike early on, as people get infected because the infection rate is high, right? Because the infection rate is very high. Maybe we put 10, let's say. That makes it even higher, right? This is such an infectious disease, right? And it's like, it just, for example, it gets suspended in the air for, you know, weeks at a time. And if someone is just walking by, just, you know, talking or sneezing, that droplet is suspended everywhere, right? So it stays there for a long time. So that would increase beta. Okay, so let's go back to 0.5, for example. Now I want to see the effect of gamma, okay? So what happens if a disease, so 1/14 is like, you know, number in between. So what if the people get infected only for 1 day? So we put 1/1 essentially. Let's say 2 days. People get infected for 2 days only. Remember, gamma was 1 over the length of infection, okay, per days. Okay, so 1/2. So on average, people get infected for 2 days. What would you expect to happen? If people barely get infected, well, they're not going to have time to pass the infection, right? Agreed? So we expect the red curve to go down, right? Okay, there you go. It went down. There's still a slight bump. So if you plot in semi-log y, you're going to see a bump over here. But because it's barely infectious, right? Sorry, because it is very infectious, 0.5 for beta, but the length of infection is so short, it barely has time to infect people. And that is equivalent to a disease that is very lethal. Okay, although we're not accounting for people who are dying over here, but a very lethal disease doesn't have a chance to infect people. If you think of MERS, the Middle Eastern Respiratory Syndrome, and SARS, those were very lethal. We barely had, you know, a few thousand people dead across the planet, but it didn't infect anyone, right? Because people didn't have a chance to infect people, other people. What we have today is really terrible. It's like, it's a highly infectious disease and it lingers for a long period of time. So let's take gamma equal 1/20. Let's like people get 1/30. That's like people are miserable for a month, right? So what you get a very extended, you get an increase in the peak. We went up to 80%, but you get a very long period of infection, right? A very long period of infection, right? So this hopefully gives you a sense of how diseases spread, right? We're not, you know, I'm not in the infectious disease business, but, you know, as chemical engineers, as engineers, I think we can pretty much apply our knowledge of ODEs and conservation to at least kind of think about these problems, right? And when we talk about flattening the curve, you see that peak at 80%. What we want to maintain that peak below capacity, right? And now you see how things like infection rate, length of people length of recovery could affect flattening the curve, okay? And if you wanna kind of play around more with these numbers, I have this cell at the bottom, excuse me, that has an interface that you can, hold on, it's not, oh, so see, I changed the order over here because everyone convinced me otherwise. All right, so now, you know, if you play around with beta over here with these sliders and the recovery days, you can play around on your own, see how you can flatten the curve, how you can try to make sense of this disease, right? Okay, so we run for 12 months, we change the infection rate, and then you change the number of recovery days, long recovery, you see how can it expands, etc. All right. Okay, so hopefully this was fun and entertaining. And I'll go over very briefly over a few other slides before we switch to boundary value problems. So now hopefully you are motivated to understand how to solve systems of equations. This is real stuff. It's not like things that are esoteric, not applicable. This is very applicable, okay?
So I have a question before we move on.
Yes, Connor.
So if we wanted to start looking at the death rate, how?
Okay, I'm gonna talk about that.
Like,
okay.
Because now we've got like 2 exits out of the infection rate. How would we go about working with that?
Okay, so you define another compartment, call it death or dead people, right? And then you just have a rate of change of the dead people coming from infected, for example, and you just add a coefficient. And then the depletion rate out of infected, some of them are going to go to recovery and some of them are going to go to dead, right? So you add one more variable, one more ODE, and go ahead and solve it. This is a great idea. What I'm going to propose next is my efforts at trying to understand how we flatten the curve. So like you said, it's possible to flatten the curve with dead people. Sorry, it sounds just horrible, right? But you know, that's not the intention. The intention is, you know, more people dying means that the disease has less opportunity to spread. But as I see from COVID, I don't think that the number of dead people is going to be a very valuable variable to track. What is more important, in my opinion, is to track the effect of social distancing, because if eventually what we want to manipulate beta. It looks like gamma is hardly, we cannot manipulate gamma. Gamma is manipulated by, you know, the disease gonna make you sick for 2 weeks or longer. Well, we can't touch that. We can't change that. You're gonna carry the infection. Even if you're feeling better, the infection is still in there. It takes your immune system a fixed time to get rid of that. And the rate of people dying from the disease is so low that's going to make an insignificant effect on the curve. I think what's more important is social distancing. So what I'm going to share with you next is a model I was working on before, as I was putting these lectures together. I call it the SIRD, S-I-R-D, for susceptible, infected, recovered, and distanced people. So what I did with this model is define a population P that contains free roaming individuals, those are the susceptibles, and people that are socially distant. So that entire population has people who are socially and physically distant, so staying at home, you know, like me and my family, like all of you, right? And some people who are still susceptible, moving around, you know, healthcare workers, people at the grocery store, Amazon delivery people, etc. So those people are still moving around. And then I define a rate of people moving from susceptible to physical distancing and back. And that rate depends, those rates could depend, for example, on saying, hey, you know, federal policy says everyone stays at home. So you're going to see a lot of people moving from susceptible into distance. And then you see maybe, you know, summer is coming up, people want to go hiking. Now you see a lot more people coming out of distancing into the susceptible category. And now what follows essentially is the remainder of the SIR model, from susceptible to infected and from infected to recovered, okay? Now the equations, all we have to do now is track one more variable called D for distance, and then account for the rates of change correctly. So ds by dt, you're still draining people to be infected at the rate minus beta si, but also you have people leaving susceptible at the rate delta 1, and people entering susceptible at the rate delta 2, right? So you have delta 1s going from susceptible to distance, and delta 2D going from distance to susceptible. Again, you are not, so FYI, this is not a course on ODEs. You're not responsible for writing ODEs, but I think this is a great opportunity to kind of have these ideas fixed in your brains forever, for the rest of your career. I think it would be very valuable. And then you just have an additional equation for the distance, which is essentially whatever's coming into the distance, that's delta 1s, and whatever is leaving is minus delta 2d, and the rest is the same as the SIR model. So, I'll have a lot to talk about this model, so I'm gonna let you go ahead and study it by yourself if you follow this link. So if you all follow this link now, you're gonna crash my server, but you can try to. But if you follow that link, what you're gonna find, what you're gonna see is a web app that implements ODE/int, just like we did in class. This is nothing different, nothing mysterious. This code is only a few hundred lines in code, nothing different than what we did in class for the SIR model. However, I have more options in the user interface. There's a description in the model, in the page, and there's a set of slides at the bottom. Just follow that hyperlink. You can study it on your own. But the cool thing over here is you can play around with a bunch of parameters. And a couple of cool parameters, you can add the discovery of a vaccine. So let's say you discover a vaccine after 6 months. Probably have to rerun this. It will take a minute. to initialize the Docker image, what's called the Docker image on the server. Anyway, so with this web app, go ahead and feel free to play around with it after you read the documentation. And what I have is a dynamic model for social distancing. One model for social distancing is to say, if the rate of infection is below a certain threshold, then let people go out. And then when we reach a certain threshold, then people will socially distance, right? Wouldn't that be a little bit more effective than shutting down the entire economy and having everyone being socially distant? What if we can achieve the same peak with only 70 people, 70% of the population being distant? So that model attempts to at least answer that in a idealized environment. It will take a little bit to load sometimes, so just be patient with it. At Saad.html, let's see. Anyway, if it doesn't run now, feel free to go and execute it at your own time. And if you have questions, we can talk about that later. But anyway, the point is, these are serious things we're doing, right? This is not just these are not just toy problems. They're realistic things, okay? And before I give you a break, we'll just finish off with a couple of slides on ODEs. This is another system of ODEs related to chemical engineering. This is typically the example I would go through in a non-COVID outbreak year, okay? But this contains kinetics. It's the same idea. You have a compartment A going to B, that's a reactant A going to a product B, and then B also reacts at a certain rate, right? So it's no different than the COVID model, and the analogy is very striking. Now, one more thing to think about is we've only touched so far on first order ODEs. What if you have an ODE like this one? This ODE describes the rate of change of position of a particle moving in a highly viscous fluid, okay? So, excuse me, just like we did the example of the parachutist early on, moving in the atmosphere subject to drag, similarly, a particle moving in a high viscosity fluid is subject to this equation where x is the position relative to the initial position of the particle, and as it moves in time, it is subject to drag and gravity. So I want you to take a minute and think of a solution strategy that we would use to solve this problem numerically. I'll give you 1 minute. Because obviously in life, you're going to encounter high order ODEs, right? Not necessarily just first order. You got about 15 seconds. Okay, time. All right. Hey, Brendan, do you have a suggestion?
My thought was maybe using like a forward difference.
Okay.
Using the difference between dx and dt on different points.
Okay. Yeah, just putting a approximation for the second derivative in time, right? Okay. That's certainly one option. But what about another option? Let's see. Garrett, do you have any ideas? Beyond just discretizing. So Brendan said we just discretize this equation like we did. We use a finite difference formula for the second derivative and the finite difference formula for the first derivative and just integrate in time.
So, I mean, I was thinking you could use substitution to write it in terms of x prime. So
okay. Yes,
you could say x1 equals x and then x2 equals x prime,
okay,
which is
yeah.
x1 prime.
Okay, so yes, exactly. So rather than going to second, third, and fourth, and fifth order approximations, what we can do in this case is essentially just turn this second order ODE into system of two first order ODEs. And this is done by taking essentially the, hold on, let me get back to the slides. If you define, so focus on the left set of the slides over here. If you define dx by dt as its own variable v, so you write dx by dt is equal to v, and then you substitute v into the governing equation, what you get, everywhere you have dx by dt, you turn it into v. So that second order ODE becomes a first order ODE in v. So you get dv by dt equal g minus alpha v, and then you get dx by dt equal v. So you get a system of two equations that are coupled, but they're both first order, okay? And there's tremendous benefit to that. At least programmatically, it's much easier to implement integrators for first order ODEs rather than having to generalize and do second and third order, et cetera. There are other reasons, but this is what you should think about. First and foremost, when you have a high order, a system of an initial value problem with a high order ODE, the first thing to do is order reduction. And what you do with that is simply substitute your first derivative, call it a variable, then substitute that first derivative with that variable name, and then keep going on, and you reduce a high order ODE into a system of first order ODEs. On the right hand side of the slide is yet another example. They're just obvious now. Once you turn it into a system of ODEs, you can use ODE int or just do it by hand like we did in class. I'll give you now a 2-minute break before we start on our boundary value problems. All right, go ahead, stretch your legs, get some water. Make sure you stop your video and mute your audio. All right, I'll see you in a second. All right, I am back. Hope you're back too. Okay, so next we are going to look at boundary value problems. and as opposed to initial value problems, what we've been discussing so far. And if you remember last couple lectures ago, we talked about the difference between initial and boundary value problems. Initial value problems, they're propagation problems. Typically, they have time in them. We start from an initial state and things happen. They react, they mix, population changes, right? And evolve over time. Boundary value problems are a different, monster. And I've been trying to think of a kind of nice, realistic example that I can give you about boundary value problems. This is what I came up with, and actually it's a true story. So as we've been quarantined and trying to avoid people, we've been avoiding going to the playgrounds. Luckily, we have a nice big-sized yard, and we've been throwing water balloons from the deck with my 2-year-old. But also he gets sick and tired of the backyard, so we have to go out. And so I discovered a little watershed, like a container or something for the city, for the public works. And it has a very nice, well-groomed area with trees and grass and some trucks over there that no one apparently likes to go to. And so we ended up turning that into our little private park. We go and run around, do picnics over there, and my son gets to see the trucks, etc. On the way there, the other day, there was one of those electric poles, and the wooden ones. And I looked up, and it was kind of broken. But then they had like a support pillar to it, and there were a bunch of suspension cords. It looked like just a disaster over their cables intersecting each other. And then my son, he was like, I want to hold it. I want to hold it. I was like, what are you going to hold? And apparently one of the tension cords was completely loose. It was just like dragging on the ground. And I ended up calling Rocky Mountain Power for it, but he grabbed it and he wanted to like drag it. And so it took the both of us to just kind of try to lift it. But then it hit me as the cable was kind of dragged down at the bottom, and then we lifted it a little bit. And then lo and behold, the shape changed, right? Then I lifted it higher and the shape changed. And then I dragged it a little bit further and the shape changed. And that is a boundary value problem, because the shape of the cord in between, okay, depended on the position of one of the ends, right? In fact, both ends. One end was fixed. The other end, I was able to move it up, move it down, etc. And when I pulled on it, I changed the tension a little bit, but that's not really a boundary condition. But the position at the boundary affected the shape and the interior of the domain. And so the physics that govern the shape of the cable were affected by the boundaries of the cable. That's the best example I could come up with in terms of something that we can relate to. I have a more engineering example next, but the idea of boundary value problems is that you have a region of space and an environment where you have some physics going on, okay? But as you change the conditions at the boundary determine the final solution of how those physics evolve, okay? So again, think of the cord example, that tension cord. When the shape of the cord, the physics that govern the shape of the cord changed, the answer changed based on the condition of where I put the cord, okay? One classic example that I always give in this class is a heated rod fixed at 2 temperatures. Again, think of this like, let's say you have a spatula immersed in boiling liquid, and somehow you have like an ice cube, for example, on the other end, and you want to look at the temperature inside the spatula, right, at steady state. Water's boiling, it's a constant temperature, and then the ice cube is constant temperature. So you have 2 fixed temperatures at both ends, not necessarily equal. One of them could be larger than the other, higher than the other, doesn't matter. But then that rod is also subject to an air environment at a certain temperature. We've been calling this T infinity. Now, if you remember, one of the first examples we did when we were doing linear solvers, if you remember the heated rod, this is it, we're coming back to it. And I had told you in the beginning not to worry about how we obtain the systems of equations that we solved iteratively. Now we are gonna learn how to obtain that system of equations, okay? Now the equation that governs the temperature in the rod, and you will learn this in heat transfer, I'm going to give you the equation right now, so you're going to have to take my word for it. Again, we're looking at the distribution of the temperature inside the rod, okay? At every point in the rod, what is the temperature? If you know the temperature at both ends of the rod, if you know the equation governing the temperature in between, solve for the temperature at every point in between. Okay? Now that equation is given by the second derivative of the temperature in space. So you have d2 by dx, d2t by dx squared equal some bunch of coefficients we'll talk about in a second, times t, the temperature at any point x, okay, minus t infinity, that's the temperature of the surrounding air. Now, obviously, what is going to govern the temperature change in that rod, going to have to do how well the rod conducts heat, right, from every molecule to another. How well are molecules sensing each other's vibrations, right, on average? And then also how effectively is air adding or removing heat from the rod. So let's assume for a moment that both temperatures at the left and at the right are the same. Let's say 500 degrees. Then at steady state, that entire rod is going to be at 500 degrees. Then you bring air at 300 degrees. Now, there is a rate at which you do air at 300 degrees, then obviously it's going to lower the temperature in the middle of the rod. Now, what if you bring water at 300 degrees? Obviously, water is more effective at transferring heat than air is. And we would expect more of the rod to reach the temperature of the water than that of the air. That coefficient is called H in that equation. The coefficient that tells us about how well heat is conducted inside the rod itself from one point to another is called lambda. So we have H over lambda, and P and AC are related to the geometric properties of the rod. What we're going to do next, we're going to replace all of this combination of parameters with just one number, okay, that we're going to manipulate. Now I have a bunch of other things that I'm putting here just to be rigorous. But again, you're not responsible for deriving an equation like this, but you're responsible for understanding how to solve it numerically, okay? So what we're going to do, there are a couple of methods we can use to attack this problem. We're going to learn about the finite difference method because I think that is more effective for boundary value problems as you go into doing partial differential equations later. Okay, with finite difference methods, we're going to idealize this rod as follows. We're going to call the heated rod. We'll give it this kind of gray rectangle, and we know the temperature at the left, and we know the temperature at the right. And we're going to write this governing equation, and note what I did. I replaced HP over lambda AC by capital H. To me, this is just a number. And what we're going to test now, when we start solving this equation, we're going to test low values of H and high values of H and intermediate values of H. What happens to the temperature profile? And T infinity obviously can be higher or lower than either T left, T right, both of them, etc. We're going to look at all of these options and compare to what intuition tells us, okay? So now your first activity, you got 45 seconds, just in words, based on what we did with initial value problems, what would you suggest the first step to be? Remember when we first did the initial value problems, what we did with time. So what would you think the first step in trying to solve this boundary value problem numerically should be? Go. You got 10 seconds, 7 seconds. Okay, time. All right, Abigail and Connor, you were talking and moving your hand, so I think you have an answer.
So wouldn't it be that the first thing that we should do is divide the rod into equidistant lengths?
Yes, yes. They don't have to be equally distant, but in this course, we're going to take them equally distinct. But yes, the first step is to discretize the space domain into n equally spaced points, okay? Just like we did in for initial value problems, we took the time domain and discretized the time domain into what we call time steps. Right now, we're going to discretize this into these physical steps of size delta x. And then what we're going to do, we're going to assign a value for x at each of those points. Now, that value is going to be helpful if your source term depends on the location and also for plotting purposes, okay? So we may as well just do that. Programmatically, we can just do this with Python, with linspace, right? So x1, we're gonna call the first point point 1 and the last point n for n points. Okay, x1 is obviously 0 and xn is L, the size of the domain. Then x2, x3, and so on. We did this something similar when we were doing iterative solvers as well. And the spacing is delta x between the x's. Next, we're gonna assign a variable for the temperature value at each of those points. Now, we do not know the temperature at the intermediate points. We only know it at the left and we know it at the right, but we don't know it in between, right? So we're just gonna assign a value, T2, T3, T4, and so on, all the way to Tn minus 1. We don't know what those are. Our purpose is to find those discrete values, okay? That's the goal of solving this system, this equation. All right, so next, this is our equation. My question to you is this equation valid at those discrete points? And you should know the answer in a second. I'll give you 30 seconds. If not valid, why would it not be valid? So this equation governs the physics inside the entire rod, okay? Which just shows a set of specific points in the rod. And the question is, does that equation govern the physics at those points? So what do you think? Let's see. Kevin R. Ramirez, do you have an answer? Unmute.
I was thinking about like it might be, but then I'm thinking like about the endpoints where it, like, you know, we have to like.
So forget about the endpoints, okay, for now. At the endpoints, it's given to you, okay? And if we can satisfy it, that would be great, but that's what a boundary value problem is. So we can talk about the limits of the ODE as it approaches the boundary, etc. But that's a math question. Discretely, at least in the interior of the domain, do you think the equation is valid?
I think so, yeah.
Yeah, absolutely, absolutely. Why would it not be valid? Right? We started by saying that this equation governs the physics inside the entire rod. So it would cover it at any subset of points in that rod. So what that means is that we can apply the exact equation at each one of those points. So at point 2, we could say the d2t by dx squared at point 2 is equal h times t2 minus t infinity, right? And then we could say d2t by dx squared at point 3 is equal h t3 minus t infinity, and so on and so forth. Agreed? So that's what I'm getting to. Now, I'm going to take this representative point, point I. Point I could be 2, could be n minus 1, could be 4, could be 15. Just a representative point I, okay? Now, based on what we did with initial value problems, so far we're following the strategy we did with initial value problems. What is the next step to solve this equation numerically? Just describe the step. You don't have to give me a solution, okay? Just describe it. What do we do next?
You would just use like a 4 difference formula that we already know, right? And evaluate it at I and then replace the left-hand side.
Okay, so okay, yes, but you chose forward difference. There's no reason to choose forward differencing because a forward difference is going to be a little bit costly. What we're going to stick with right now is to say we're going to approximate the derivative, okay? But rather than forward difference, I would use a different kind of difference, and that's for you to answer now. You got 1 minute. I want you to dig through your slides. because we did this before. We did approximate a second derivative. Okay, so what Emily was saying is next step we have to approximate the derivative, okay, discretely using the points, the discrete points 1, 2, and 3, and 4, etc. So for any point I, for arbitrary point I want you to approximate now the second derivative. Use your notes, go back to your notes. We did this when we were doing finite differences, okay? Go ahead, I want you to fill in the blanks. Yes, Paul, you are correct. Find an equation relating I, you're relating the temperature at I to the temperature at I plus 1, not I to I plus 1, but I think that's what you meant. But what is that relation, right? So Emily was saying do the forward difference. There's a more natural difference for second derivatives that gives us second order accuracy at a lower cost.
Would that just be
Yes, there's a lot of noise. Who was that? Was that you, Nick? Yeah, there's okay, yes. So Nick was suggesting we do a center difference, and yes, that's the natural formula you would use rather than biasing. If you went for forward difference, what are you going to do when you get Tn minus to Tn minus 1? Where are you going to get the extra point from outside the domain, right? You don't have that point. A center difference in this case beautifully fits for the interior points, because at T2 it's going to use T1 at most, and at Tn minus 1 is going to use Tn, and both of those values we know. Whereas if we're using forward and backward differencing, as you reach one of the ends, you're going to have to use points that we have no information about. We can extrapolate, but that's risky because we have no information beyond the domain of this system. So we'll go through the next couple of slides before I let you go. So what this means is that we get this second, this center difference formula for the second derivative, which was d2t by dx squared is ti at point I, relates ti minus 1, ti, and ti plus 1 in the following manner. The right-hand side is still in terms of ti. We're not going to worry about that. Now next, we just multiply by delta x squared and move all the unknowns to the left-hand side and everything that we know to the right-hand side, okay? So this results in the following representative equation at any point I. So ti minus 1 minus 2 plus h delta x squared ti plus ti plus 1. It sounds silly when I'm just reading equations to you. So I'm hoping that as you're doing the math, this will make sense. You'll get a chance to do this in a second. So now we have all the ingredients. I claim that we have all the ingredients to solve for the unknown quantities T2, T3, all the way to Tn plus 1. Explain why we have all those ingredients and what do we do next? What is the next step? And if you have an answer, feel free to volunteer. So although this is a group activity in class, it would have been, a group activity, but feel free to volunteer now so we can make headway on time.
So if
Yes.
we treat the boundaries as ti minus 1 and ti plus 1, then the only unknown is ti.
Okay, but still, so I claim that we have all the ingredients, that this equation is actually not a single equation, because this equation is only a representative at any point in the interior of this domain. Okay, so we have all the ingredients by saying we have all the xi's, we have the boundaries, and then we have all the equations in the interior of the domain. But what do we do next? Do I have any takers?
Make a matrix.
Okay, so how do we build a matrix, Katrina?
So then, so we have like unknown quantities like 2t2, t3. So like you have like one where it's like t like 0 all the way to tn minus 1.
Okay, or t1 to tn. So in other words, okay, so in other words, I agree with Katrina, but there's one more step to kind of untangle what you're trying to say, is that this is actually a system of linear equations. And to see this system of linear equations, before I let you go, I want you to go ahead and take this representative equation at point I and apply it, okay, everywhere in the domain, okay, from point 1 to point n. Now be careful, at point 1 and point n, we know what the temperature is. So there's no need to apply the equation, right? But then I want you to write out the equations at point 1 for temperature, at point 1, point 2, point 3, and point n minus 1 and n. I want you to just write these 5, just spell them out, okay? Take this equation, okay, and spell it out so that we can see the linear system. Okay, you got about 5 seconds. I know you're rushing to write it down, but once you write one of them, it becomes clear. Okay, so before I rather than taking answers from you, I just want you to compare what you got to what I have. So at point 1, the equation is simply T1 equal T left, what's given to you by the user or what's specified by the physics. Agreed? That's the answer at point 1. At point 2, I equal to, you simply put I equal to in that equation, and then you get the relation between T1, T2, and T3. Okay, and that relation looks like that's the template up there. Then at point 3, you get the relation between T2, which is Ti minus 1, and T3 and T4, and so on, all the way to the before last point, that's n minus 1. So you get a relation between n minus 2, n minus 1, and n. And finally, at the last point, Tn is equal to T right, which is also given to you. Now, you should see that this is a system of linear equations. Why is it linear? Because the unknowns show up linearly. What are the unknowns? They're T2, T3, T4, T5, T6. And there's a reason I include T1 and Tn in the system programmatically, because that returns the boundary conditions in the solution. We'll talk about that when we program this. But essentially, that's what I'm going to leave you today. Is next time we're going to take this and just turn it into a matrix vector form, and we know how to solve that, okay? Because we already did this. So now you not only know how to solve the system of equations, you know how to derive it, all right? So with that, I will let you go. If you have any questions, go ahead, and I'll leave the floor for you a couple of minutes if you want to ask any questions. And again, for meetings, etc., just ping me as needed, and we can do Zoom meetings as necessary. Emily, you have a question?
I guess I'm kind of jumping the gun, but you would just use either like the Thomas algorithm or the Gauss-Seidel method, because this is diagonal in the end.
So we will get a tri-diagonal system of equations, and preferably we would use the Thomas algorithm. We're not going to use Thomas now. We're just going to use NumPy solve .lenalgebra.solve, because the focus here is on deriving the equations, not just solving them. We just want any tool to solve them, right? But building this system of equations, that's what's important. So we started with a differential equation, and now we turned that into a system of n equations that are linear, okay?
Okay.
Quick question.
Garrett.
Could you set T left equal to T0 minus 2T1 plus T2 over delta X squared?
No, because that is a specified boundary. The value at the boundary is not obtained from the interior. Okay, the value at the boundary needs to be specified. Okay, otherwise, so if you integrate this, analytically, you would need 2 boundary conditions. Okay, essentially at each boundary, you'd need 2 boundary conditions. But getting the boundary value from the interior, it's not a boundary value problem anymore. Now, what you would do at the boundary, you would get the flux, how much heat is escaping, okay, at the left boundary or at the right boundary, okay? But over here, the situation is, so what you're describing is a different situation, completely different situation.
Okay.
So what you're describing is more like a propagation problem, more similar to an initial value problem, okay? But it doesn't describe this. There's also, out of the theory of differential equations, this type of equation is what we call an elliptic equation, where any change at one point in the boundary is going to affect all points almost instantaneously. So you have to have these 2 boundaries, okay?
So I'm actually just curious, just on Python in general. A lot of the things that we were doing with like the models, for example, if we like adjust one variable and show how that affects, you know, a XY plot, I was wondering if there is any like 3D graphing modules for Python that you could recommend, so you could like kind of do that.
So are you talking about the interactive?
Yeah, like rather than doing it interactively, like graphing, say the curve with respect to beta.
Yeah, you can use, so advice to you, I do not like 3-dimensional plots. I would rather have 2D contour plots for different variables, because you're trying to plot a 3-dimensional plot on a 2D screen. It really doesn't tell the entire story. They're just, when I see them in papers, my first comment to you know, the authors, like, please don't do 3D plots. They look cool when you're like trying to show off something, but they're hardly useful, right? So I mean, yeah, if you want to do something cool to show off, there's some 3D plotting in Python. In fact, I've never wanted to use that. I don't even know what the library is called, because I always prefer to use a contour plot. So even if I have a 3D structure, so what Brendan is saying is, rather than plotting only for changing beta and plotting and changing beta and plotting, why don't we plot versus several values of beta, like in the SIR model, right? That's going to give you a curve. It's just going to be annoying to look at, because you have to rotate it, and it's going to be kind of skewed in perspective, so you don't really know the scale of the change. I would rather, you could create a plot like that, but then do contour plots instead, for example, where you show the change in the variable in the beta as you move from one contour to another, okay? But that's kind of beyond, yeah, a good question though. All right, other concerns, disagreements? Tyler is asking if we have a quiz today. No, I forgot to put a quiz today. Thank you for reminding me, Tyler. I'll put one on later. But make sure you're always tuned to Canvas, because I'm making all announcements there. Okay? All right. If no further questions, I will let you go. And I will see you on Thursday. We'll try to finish off with boundary value problems on Thursday, so that the Tuesday after we can do some wrap up and fun things before you leave off for the final exam. Okay? Thank you for your attention. Thank you. Thank you. Bye-bye. I'll see you on Thursday.